Welcome back to what might be our last lesson, maybe our second last lesson on this topic, and we are just working through the tutorial. Remember, try each question before looking at the solutions and then let the video play again and see how you went. Okay, let's dive straight in. So we're on page 45 and we're looking at question number 3. Now this one does not involve any formulas. What it does tell us is that we're dealing with a geometric sequence. Now, if three terms are in geometric sequence, then we know that x divided by 6 must be the same as 54 divided by x. Right, that divided by that would give us r, the common ratio, and it's common, so that divided by that must be the same. Right, it makes sense, it always makes sense. If we multiply these two together, we're going to get x squared. And here we're going to get 324. 54 times 6, 324. Sorry. Now, 324 is a perfect square. Don't forget, though, that when you square root, you could have plus or minus 18. Right. And so there's two possible values for x. And you'll notice that if x is 18, then our sequence looks like this. It looks like 6, 18, 54, and our common ratio would be positive 3. But if x is negative 18, then we still have a common ratio. This time the common ratio is negative 3. Okay, so both answers work. Here's a word problem. Alex decides to include both swimming and running in her exercise plan. On day 1, Alex swims 100 meters and runs 500 meters. Each day she increases the distance she swims by 50 meters and the distance she runs by 3.5% of the distance she ran on the previous day. Right, so let's see, how far does she swim on the nth day of her exercise plan? Now the safest thing to do here is just to write down a few terms. On day 1 she swims 100. All right, and then on each subsequent day she swims 50 meters more. So on the next day, 150, and on the next day, 200. And what sort of sequence have we got here? Yep, we got an arithmetic sequence. So on the nth day, remember the formula for the nth term, a plus n minus 1 lots of d. On the nth day, she will actually swim, let's have a look, 100 plus n minus 1 lots of 50. And that actually comes to 50 times n. And then we've got a minus 50 here and a plus 100. So 50n plus 50. That's actually how far she swims on the nth day. Let's just test it for kind of day 3. 3 lots of 50 would be 150 plus 50 would be 200. There it is. Okay. Right. What about the running? Well, on day 1, she runs 500 meters. Now, the next day, she runs 3.5% more. So we want to increase that by 3.5%. We want 103.5%. Now, 103.5% is actually 1,035. So what we're going to do is we're going to multiply that 500 by 1,035. Just to reinforce that, this number here is actually 103.5%. All right. So on the next day, she runs 3.5% further than that. So what's going to happen is we're going to multiply by 1,035 again. All right. And I think you can see what we've got here. We've got a geometric sequence. Right, and on the nth day, so on the nth day, she will run, this is her running, A times by R. Now R is 1,035 to the power of n minus 1. That's how far she'll run on the nth day. The next part of the question says, by the time she has swum, she's done 12 days of her training. Calculate the total distance that she's swum and the total distance that she's run. Now, when we hear the word total, what are we talking about? Absolutely, we're talking about the sum. So now, for the swimming, remember the swimming one was arithmetic, so it's going to be n over 2, 2 lots of A, plus n minus 1 lots of D. That's our formula. And after 12 days, the total distance that she would have swum will be 12 over 2, 2 lots of A. You might remember that she swam 100 meters on the first day, plus 11 lots of D. And D, remember, was 50 meters. Okay, now 11 times 50 is 550, 650 times by 6, right? Let's just make sure that we've got that right. 650 times by 6, 6 times 650, and we get 3900. That's 3,900 meters. 3,900 meters. That's how far she has swum altogether in 12 days. Remember, in a kilometer there are 1,000 meters, so you could also write this as 3,9 kilometers. Okay, let's look at the running. Well, the running, we need to use this formula because we're going to add up some terms of a geometric sequence. A r to the n minus 1 over r minus 1. Okay, and remember on day 1, 500, A was 500. So the sum of 12 terms is going to be 500. Then we've got 1,035 to the power of 12 minus 1 over 1,035 minus 1. Okay, and let's just have a look at what all of that comes to. It in fact comes to 500. Brackets 1,035 to the power of 12 minus 1 divided by 0,035, and we get 7300,98. Right, basically 7,300 meters, 7,301 meters. All right, and that in fact could be written as 7,3 kilometers. Okay, right. If you haven't tried the next questions, remember to pause the video and then let it play again to see how you did. This one we're evaluating something up to infinity, all right, a sum to infinity, so it must be geometric, all right, and it must converge. Let's just see what the first 3 terms are. Remember, sigma notation, always write down 3 terms. What we get is we get 2 over 3, then we get 2 over 9, then we get 2 over 27. If you take any term and you divide by the term before it, you'll see that you get a third. R is 1/3. This will converge. Why will it converge? Well, it will converge because R is between -1 and 1. And so we can use our sum to infinity formula. Remember our sum to infinity formula, A over 1 minus R. Okay, and A is 2/3. And we're going to divide that by 1 minus 1/3. Right, and so we actually get 2/3 over 2/3. Lo and behold, we actually get 1. All right. A reminder that it never gets to 1. It just gets closer and closer and closer and closer to 1. Right, we'll just quickly demonstrate that with a calculator. So what we've got, if we just add some of these just on the calculator, if we get 2/3 and we go plus 2/9, 2/9 plus 2 over 27. So far, we've got 26 out of 27. That's actually quite close to 1. All right? Let's add in the next term. If we add in 2 over, now 3 lots of 27 is actually going to be 81. 2 over 81. Right? And now notice it's actually getting closer and closer to 1. Okay. Takes a while. The next one would be 2 over 243. But it gradually gets closer and closer to 1. Let's look at the next example. We've got a whole lot of cans that have been stacked. There are 30 cans, then 29, then 28. how many cans will there be in the nth layer? This is layer 1, layer 2, layer 3. So what we've got here, we've got an arithmetic sequence where in fact we are adding -1. Our common difference is -1. Now if our common difference is -1 and our first term is 30, remember the formula Tn is A plus n minus 1 lots of D. All right, so the number of tins in the nth row will just be 30 plus n minus 1 lots of -1. -1 lots of n minus 1. That can simplify quite nicely because we're going to get a -n and we're going to get a +1. So it's actually going to be 31 minus n. Okay, 31 minus n. And so then let's just check that. In row 1, if n is 1, we would have 30 cans. Yeah. In row 2, if n is 2, we'd have 29 cans. How many rows can we make like this? Well, you can't have, we obviously need to have, in the top row, we're only going to have 1 can. All right, in the top row, we're going to have 1 can. And what must n be to get 1 can? Well, n must be 30. So we can have 30 rows. So now what we're asking is how many cans will there be if there are 30 rows? And the answer is 30 plus 29 plus ... plus 1. All right. This is now an arithmetic series, not a sequence. We're going to add them up. We could use the formula as provided, the formula for the arithmetic sum, but we could also think back to what Gauss did. What Gauss did is he said, let's write these numbers down underneath here, 1 plus up to 30. Each one of these pairs comes to 31, right? And there'll be 30 pairs. So the answer will be 30 pairs of 31. But we've added the red numbers and the blue numbers, so we wish to divide by 2. So we're going to actually get 30 divided by 2, which is 15 times 31. Right, and 15 times 31, I think, no, I'm not sure. I think it might be 485, but I'm going to test myself. 15 multiplied by 31, oh goodness, nothing's happening here. 15 multiplied by 31, 465, just as what I checked. Okay, 465. Okay, and that's the total number of cans. Okay, penduli kasi. Let's have a look at this one. It says, determine a formula to represent the nth term. Now remember, the first thing we're going to do, we're going to go that minus that, we get 2, that minus that, we get 4. This is not an arithmetic sequence. If we go 43 divided by 41, we don't get the same as 47 divided by 43. This is not a geometric sequence. What must it be? There's only one more type, and that is quadratic sequence. Let's write down the first differences. I'm just going to write the terms down again here. 41, 43, 47, 53, 61, and 71. Those are the original terms. Now let's write down the first differences. 2, 4, 6, 8, and 10. Those are the first differences. And they carry on, obviously. Those are the first differences. Now let's write down the second differences. The second differences are just the differences between the differences. 2, 2, 2, and 2. Those are the second differences, and they also carry on. Now, this is where we need to have remembered some formulas, because the only formula we get given is this rather boring little formula that says we're dealing with a quadratic expression, something with n squareds, n's, and numbers. Okay, now what we need to do is we need to be able to find these three things. A, B, and C. Okay, we're hoping you remember how. How do we find A? Well, A is the second difference divided by 2. The constant second difference. So that constant second difference, this number over here, divided by 2. Okay, so in fact, A is just 1. The next little trick that we need to remember is that 3 lots of A, that's A, plus B will be equal to the first term of the first differences. It will be equal to 2. And although these numbers are both 2, this 2 that we're putting here is actually that 2 from there. Right, now there's only one variable left here. So if we subtract 3 from both sides, we get that B is negative 1. And then the last thing is that we can use any term, all right, and maybe the most obvious one is if n is 1, then we get A plus B plus C, and that must be the first term of the entire thing. So in fact, we know that A, which is 1, and B, which is minus 1, and C, they must all add up to 41. Okay, and if we look at that, that is the first term of the entire thing. And the only variable in there is 41. Okay, so now we actually know that C is 41. And in fact, our final answer, we know that the nth term formula for this particular thing is 1n squared minus n plus 41. Okay, now we go into part B, and this is a really interesting thing. It says that this formula actually produces prime numbers. Okay, now that might surprise you because there's no such formula that produces all the prime numbers. But this one produces prime numbers up to 40 terms. So in other words, if n is 40, we still get a prime number. Okay, but watch what happens if n is 41. T41 is actually going to be 41 squared minus 41 plus 41. And in other words, it's going to be 41 squared. Now, 41 squared is not a prime number because it's 41 times 41. Okay, so it's not prime. Okay, then they say determine the units digit of the 49,998,998th term. Now that seems very strange, but let's look at the units digits of these terms. They actually go 1, 3, 7, 3, 1, 1. Okay, so let's just see. There's a pattern here. All right. The first one ends in 1, the next one ends in 3, then 7, then 3, then 1, all right, and then the next one, if we had to work out the next one, okay, so this is 1, 2, 3, 4, 5, 6, if we had to work out the 7th term, okay, we'd get 7 squared, which is 49, minus 7, which is 42, plus 41, we'd get 83. It would end in 3 again. And what actually ends up happening is that these digits just repeat like that. Okay, and now let's see how long the pattern takes to repeat. There, that's the pattern. So every single 4th term will end in 3. Okay, and now 4 does go into 50 million. Okay, 4 goes into 50 million. We know that, all right? So the 50 millionth term would end in 3. And so the one before that, with 999th, would end in 7. And the one before that would end in 3. Okay, so we're just applying a kind of a pattern here and trying to see where we are in the pattern. Okay, quite an unusual question. I wouldn't worry too much about it, but let's end there. Next time, I'm just seeing how much more we've got. We've got a few more questions. I think the next lesson will be our last lesson on this topic. Before you watch the video for the last lesson, make sure you've tried the last few questions. Have a great day.